Well, before we continue with the lecture, raise hands who can tell me in 10 seconds what is the difference between a fermion and a boson. Yeah.
Fermion starts with F, boson starts with D.
Okay. First hand up. Okay. So, say hard.
The Pauli law, I think, because the fermions can have the same energy, but bosons can all have.
And why is that?
Because of the Bose fermion distribution and the other one, I think.
Yes, correct. But why?
The spin.
Exactly. So a fermion is a particle or a quasi-particle with half spin, while a boson have integer spin. Do you know why the boson statistics, it is called Bose-Einstein statistics, and why it is called also Bose-Einstein condensate? No, this is a story, not a scientific question. Well, Bose sent his paper in which he did some sort of calculations what happens with the statistics of particles which have integer spin, and came to different statistics than the Fermi-Dirac statistics, and he sent it to publication. And he was rejected. And then he sent his paper to Einstein, telling, look what happens, this is my idea, and so on and so on. And Einstein replied to the reviewer, you guys are stupid. And then they improved a little bit the paper, and that's why we call them Bose-Einstein condensate and not just Bose condensate. So these are some of 5 little stories about superconductivity I know about. Okay, so let's go back. We are actually still in the first lecture. We discussed about Peeling force, which can be determined from magnetization loops. And if we look at those shapes, we can correlate the shape of the pinning force as function of the reduced field with a type of pinning centers. And this is this seminal work of Hughes, in which he shows the following thing, that if we have, so remember again, we have from the point of view of dimension three types of pinning: volume pinning, surface pinning, and point pinning. And from the point of view of type of the center, we have normal or delta K, normal or delta K, normal or delta K. So we have, from the classification of Hughes, we have 6 types of pinning centers, which is like this. And he derived theoretically, and in his work, this actually have a reason, an explanation, these pinning functions. For normal, it's like this. So from the general formula, you see P equals 0, Q equals 2. We will talk about the maximum constant later, what does it mean. Volume delta K is this one. Surface normal is this one. Surface delta K is this one. Point normal is this one. Point delta K is this one. Let's have a look at how they look like. So this is the volume normal. So if we plot 1 minus h at power 2, it looks like this. There is no maximum, and it starts at 1. Now, if we plot for surface normal with Hughes formula without any constant, we have the function h at power 1 over 2 multiplied by 1 minus h at power at second power, and it looks like this. Maximum happens for reduced field at 0.2, and the value of the maximum is this one. So in order to have maximum pinning force divided by maximum pinning force to have the maximum at 1, we have to multiply this function with this constant, which is 3.5. So if we multiply this function with 3.5, we move this in such a way that the position of the maximum happens for y equal 1. So we will have a 1 maximum. And this is what I have done for all of those things. So we have to multiply by a constant in such a way that the value at the maximum to be 1. In such a way that we have the value of maximum pinning force divided by maximum pinning force equal 1. So this is what this constant means. Okay, volume delta K, this is the function. If we plot it, maximum is at 0.5. Surface delta K, you see that the maximum moved at 0.6. And this is the value of the maximum. This will be the constant. And the last two will be point normal. This is the value, maximum 0.33. And this is the constant. Point delta K, H, minus H. This is the maximum. This is the thing. So what we have seen? We have seen that depending on the types of pinning centers we have different shapes of that reduced field dependence of the normalized bulk pinning, and that maximum happens at different values of the applied field. Now, when you have a real data, in a real sample you have many types of pinning centers, not just one. Because of that, we have to try to fit what we have with a combination of 2 or even 3 of these types of dependencies. We will see that later when I will show you some examples. Now, the last part of the first lecture is about the other characteristic of a pinning center, which is the pinning potential, and it will refer to energy needed by the flux line to escape from the potential well created by the pinning centers. Now, the shape of the pinning of the well potential and the influence on superconducting properties, they can be modeled in several ways depending on material, strength, and distribution of pinning centers. In 1962, Anderson predicted that movement of vortices with a drift velocity v will create dissipation, and this is given by this. And dissipation occurs through 2 mechanisms: dipolar currents which surround each moving flux line, which are eddy currents, which have to pass the normal conducting vortex core, and the second one, retarded relaxation of the order parameter when vortex core moves. Now, Anderson and Kim predicted that thermal depinning of flux line can occur at final temperature, and this is called flux creep. So what we have there, we have a bundle of flux lines, which are trapped in the potential well, but because we give them a thermal energy, they can jump over the barrier. And that jumping is the flux creep, and it's characterized by some sort of Arrhenius behavior because it depends on the temperature. And this model assumes that flux creep occurs to determine activated jumps of isolated bundles of flux lines between 2 adjacent pinning centers, and the jump is correlated for a bundle of vortices of volume, which is the correlative volume, and Vc, and this is due to the interaction between the vortices. In the absence of transfer current, meaning no Lorentz force, the bundle is placed in a rectangular potential well with a well of height u0, and due to thermal energy there are jumps over the barrier with this frequency, and this is the 10th frequency, and the value of this u0 is something like 10 to the 4th hertz, which is given in the textbook of Michael Bingham. So this is the, let's say, a little bit of math. You have this in the website of the school. I will not stay much longer to this thing. So what happened in the case 1, this is the potential well in the absence of any currents, absence of Lorentz force. So the flux bundle tend to jump this way and this way. The probability of jumping in either direction is equal, so you will have a total 0 net movement of vortices in one direction or another. Now, if you apply a current, you will deform the magnetic well in such a way that for this direction it will be more difficult for the flux bundle to jump, while in this direction it will be much easier. And this is the characteristic law of this dependence, of this probability of jump. And at a certain value of current, in one direction the potential well goes to zero, and it's very easy for vortices to move in this direction. So what happens is that Anderson and Kim predicted that critical current density will be proportional with logarithm of time. And this is actually seen all the time in magnetic realization measurements, in which if you put a circulating supercurrent, that current will drop exponentially due to the thermally activated flux spring. So this is what we have, logarithmic decay, magnetic relaxation. So this is how Kim-Anderson model predicts this kind of thing. Well, you can play a little bit with this one. I've done that when I was doing my PhD. Doesn't matter, it's not very important. Second one is Larkinov-Chinikov collective pinning model, in which they deal with cooperative aspects of vortex dynamics. So the formation, in their model, the formation of the vortex lattice will be a result of competition between vortex-vortex interaction, which tends to place vortices on a lattice point of periodic hexagonal or triangular lattice, and vortex spin interaction, which tends to place a vortex on the local minimum of the pinning potential. So what does it mean? It means that vortex-vortex interaction promotes global translational invariant order, while vortex-spin interaction tend to suppress such long-range order if pinning potential varies randomly. And long-range order for a Abrikosov vortex lattice, they prove theoretically, is destroyed by a random pinning, no matter how weak it is. So if we have random pinning of a material, doesn't matter how weak it is, we will not have any more long-range Abrikosov ordering. Now, this periodic arrangement is preserved only in a small correlated volume, which depends on the strength of the pinning potential and the elasticity of the vortex lines. So correlated volume, we see, increase strongly with decreasing current density, which leads to a power law dependence of the effective pinning potential on the current density. So this is how it looks. In collective pinning, this is the dependence of the pinning potential on the probing current. And this leads to a non-normal current voltage characteristic of this form, and we get this value here, which again you can find very nicely explained in Pinkham's textbook. Now this is something which probably not many of you know about this type of dependence, which was discovered experimentally by Zeldok on YBCO films. And I did a little bit of completion on that in terms of how to use this model to get pinning potential from susceptibility measurements, which I will show you later on this week. And what does it say? So these are experiments from which Eli Zeldov get these types of dependencies. So what he says that in YBCO fields, the potential will have a cone-like structure very close to the pinning, and after that it goes exponentially. So it has a totally different shape than the square potential well, which is in Kim-Anderson model. So what he says is the effective pinning potential depends logarithmically on the current. And from that, you can get the voltage, which happens because you have thermally activated flux jumps over the barrier. So this is an Arrhenius activation energy. And also, you can also know that the voltage is also described as time derivative of the current. And if we play a little bit here with the current and do the time derivative, I showed in this paper that we have this equal to this one, and this is the end of it. And we will use that in when we will do the workshop. This was the introduction part of pinning, and now I will go to my second lecture, which is about artificial pinning, which is a normal continuation between this one. So let's see what it is here. Escape, and let's file, open, again from this one? Yeah, okay. Artificial pinning, yeah, that one. And start presentation. Okay, this was the title, but because René Flukiger will give a very extensive talk on MgB2, in which he will address also this one. Probably I will stay in this thing because this one will be covered much better than me than by René, because he works a lot in this field. Okay. We'll talk about motivation of artificial pinning, and we will talk mostly about rare earth barium copper oxide or lithium barium copper oxide films and coating conductors. Very little about these two, just to stay in time. Now, in order to use high-density superconductors for power applications, like energy-efficient devices and equipment, magnets, motors, transformers, power lines, what we need low cost of fabrication and high critical current. And at this time, if you combine these two, low cost is expressed in how much it will cost to transport 1 kiloamp over 1 meter of conductor on a 1 centimeter width of a cable. We can do several things. We can decrease the fabrication cost, or we can increase drastically the critical current which we can pass there. But what we need to do is to try to do both. And I was concentrating more in increasing critical current. Some other people around the world try to upscale the fabrication facilities in such a way that the price of the fabrication goes down. We have seen that the losses come from the movement of flux lines, Lorentz-Force permutations, and the solution for minimizing this is to block the flux lines or various types of defects, natural and artificial. And this is what was the call for something which we call now nano-engineering of pinning centers. There are many types of natural pinning centers in YPCO films of coated conductors, and these are from a very nice review paper by Fulton in 2007, Natural Materials. So we see here many types of natural pinning centers, which they occur naturally during the field growth. However, for many foreseen applications, especially in high magnetic fields, critical current still need improvement, hence we need a larger pinning force, and hence we need artificial pinning centers. Okay, so the first cost-effective method of creating like this, it's quite an old one. When I was working in Japan and I worked with Hideo Ihara, he was trying to grow to grow thin films based on the thallium system. Of course, that is now gone because thallium is too toxic and volatile to be used. But anyway, the idea was to deposit nano islands on certain materials in such a way that when we started the growth of the superconducting film, on top of these nano islands we create defects or columnar defects, columns of superconducting material, or if the superconducting film returned to growing, we have dislocation. So this is an AFM image of nano islands of silver on the substrate before growth.